In the last video, we talked about how cross-modal effects show that perceiving isn't absorbing. In this video, we'll talk about another kind of effect that shows that perceiving isn't absorbing. So here's a stimulus. You may have seen this before. The image on the top here, this patch surrounding the letter A, looks to be a very dark gray, and the patch surrounding the letter B appears to be a much lighter gray. In fact, these are pixel by pixel duplicates if you're looking at them on a screen. You can see this if you kind of cover up the central bar, maybe stick your finger in front of it, maybe a couple of fingers. You'll see that the top will suddenly appear to be a bit lighter and the bottom will appear to be much darker, so that instead of whitish, this looks like a gray, and instead of a dark gray, this looks like a kind of mid-gray. So then you'll see that they look like they match. In fact, they do match. The central area here does not match. This is in fact darker than this. But take away the central area, the rest of the pixels surrounding A match the rest of the pixels surrounding B. And there's a question, why does this happen? Why is it that the top looks so much darker if in fact it's the same color as the bottom? And the answer is that perceiving is presuming, not absorbing. So let's give a little more detail to that answer. So imagine this is a side view of the object. This is the surface that was labeled A, this is the surface that was labeled B. So if you look back at it, there's the surface labeled A, there's the surface labeled B. Now imagine you're looking at it from the side. Here's what it would look like, and we're going to add labels C and D for these two surfaces. Now here's a light source. Typically light sources are coming from above, whether they're interior light sources like lamps or exterior light sources like the sun. And here you have somebody looking at this object from the side. Now the light is striking surface A and D directly, but it's not striking surface B, C, or B directly. Indirect sunlight is illuminating them. The light is bouncing off, say, the ground first or other objects first, before maybe off of D before hitting C. So C and B, we can say, are in shadow. They're in the shadow of A and D, respectively. Now, because A is in direct sunlight and B is in shadow, the light that's reflecting off of A and striking this person's eyes is going to be much brighter than the light that's reflecting off of B and striking this person's eyes. Right? A is in direct sunlight. Bam, bright light strikes your eyes coming off of A. B is in indirect sunlight. Boom, much darker light is reflected and striking the eyes coming off of B. So if the object is in fact uniformly colored, this is how it's going to work. The light reflecting off here is going to be much brighter than the light reflecting off of here because A is in full sunlight and B is in shadow. And consequently, if this person's visual experience is based entirely on the light that's striking the eyes, that is, if the brain acts like a mere scribe and just generates an experience that matches the light absorbed by the retina, then this person would see the object as looking like this. That is, this section here would look very dark, this section here would look very bright, this would look very dark because it's in shadow, and this would look very bright because it's in full sun. But that's not how it is in the world. The object is uniformly colored in the world. The light coming off of A is only brighter than the light coming off of B because the lighting conditions are different. A is in full sun and B is in shadow. So if the person's brain wants the person to see this as it is in the world, not based on lighting conditions, but based on what this object is really like, that is, if the person's brain wants the visual experience to reflect what's actually out there in the world, that is, what the object is actually like, then the person's brain is going to adjust for lighting conditions, going to compensate for lighting conditions, and give the person an experience of a more or less uniformly colored object. And our visual system, in fact, does that. It adjusts its guess about what the object is like based on what it knows about lighting conditions, what it knows about full sun and shadow. Now, similarly, if the light striking red's eyes from A and B are equally bright, when the light is up here and A is in full sun and B is in shadow, it follows that surface A must be much darker than surface B. So think it through. Suppose the light coming from A and the light coming from B striking the eyes are in fact the same. Well, how could they be the same if B is in shadow? They could only be the same if the following is true. B is in fact very white. And since B is very white, despite being in shadow, it reflects a lot of light. Whereas A, being a very dark gray, despite being in full sun, doesn't reflect all that much bright light. So if the light striking this person's eyes from A and B is in fact the same brightness, it follows that surface A must in fact be much darker than surface B. To put it again, if surface B is in shadow, the only way it could reflect light that's as bright as what's coming off of A is if surface B is in fact much brighter than surface A is. Well, now let's suppose that's the case, that surface B is much brighter than surface A is. And suppose that the light coming in your eyes from A and B is the same. Then when you look at the object, if you don't do any adjustment, you're going to see the object as looking like this, as looking uniformly colored, because the light coming off of A and the light coming off of B is the same. But if your brain says, well, wait a second, the light coming from A and B is the same, but A is in full sun and B is in shadow, that means B must be much brighter than A is. Then you would see something like this. And that's in fact what happens here. Your brain is basically saying, look, this looks like it's being illuminated from above. Of course it's not. It's light projecting from a screen if you're looking at it on a screen, or being reflected, it's not, let's just say it's light projecting on a screen if you're looking at it on a screen. And so in fact, this B is not in shadow, but your brain thinks it is, because your brain's like, look, there's a shadow being made here. It's clear that this is kind of underneath A, so this must be in shadow. So looking back to how it works here, since the light coming to your eyes from B and A is the same, and if that's true and A is in full sun, then B must be much brighter than A is, I'm going to make you see B as much brighter than A is. So the light coming in is the same. Your brain's like, hey, B is in full shadow, A is in full sun. That means the area around B must be much brighter. So you end up seeing the object as A is much darker than B. Okay, so that's what's happening in this case. That's why A looks darker than B, because your brain is trying to make its best guess about what's out there in the world. It guesses that surface A is darker than surface B, even though the light striking your eyes off of A and B is the same, because it makes a mistake about the lighting conditions. It assumes that the light is coming from above and that B is in shadow. And the reason it makes that assumption is because light sources typically do come from above, and it appears that B is in shadow, given the apparent shape of the object. So it uses a reasonable hypothesis about the light source to adjust how it looks to you, thereby gets the wrong answer by deploying a reasonable principle. But the point here isn't that it gets it wrong or that the principle is reasonable. The point is that it's using its expectations in order to determine what you see. And that's how perceiving works each and every time. It's how seeing color works each and every time. Your brain is always using its expectations to make its best guess about what's probably out there, and how things look to you, how they sound to you, how they smell, how they taste, how they feel is always your brain's best guess about what's probably out there. Okay, so we've looked so far at the rotating mask, the McGurk effect, and two grays. In class, on Thursday, we'll look at the Ames room and sine wave speech to supplement this support for the claim that perceiving is presuming.